I hope you can all see me okay and hear me okay. I'm just adjusting my volume a bit. Can you all see me? Cool. And can you all hear me okay?
Yes, we can.
This is excellent. Okay, thank you, David. All right, so we're going to do some questions today. We're going to do some questions about energy and about energetics and what in chemistry is called enthalpy change. And you may be very good at this, but I'm going to do it because when I did it last time, some people were a little bit confused. So I'm going to show you some stuff to do with energetics. But I'm going to, first of all, I'm going to tell you something that I think is really important about examinations. So I'm going to just share my screen. So basically today we are doing practice questions on energetics, on energy, but I want you to understand something about exams, a little bit of help that I normally give to my own students. I try to help them do well in examinations by telling them what they need to know about the examinations. So here are some ideas. I will keep on telling you more about exams, but here are some ideas which you should know about exams if you do not already. The first one is that most KCSE examinations in chemistry, you have about 1.5 minutes for each mark. That is because the paper has 80 marks on it and it is 2 hours long, 120 minutes. Now that means that you need to think a little bit when you are looking at a question. You try and find out how many marks it is first. Okay, so you look at a question and it says, okay, this is worth 5 marks. If you think, okay, 5 marks, this means I can give it 7 minutes, 8 minutes approximately. And what I want you to do in the examination is to watch the clock a bit. So you try to check that you are spending the right amount of time on the question. Okay, so if you've got 1.5 minutes for every 1 mark, then sometimes there is only half a mark for a question. You think, okay, I've got a bit less than a minute. I'm not asking you to be precise, but it's important. The next one is that questions usually become more difficult through them. So if you're on question 4, the first few points are quite easy and then they become more difficult. What is important about that is that it means that it is quite easy to pick up the first few marks, but if you spend too long trying to pick up the more difficult ones, sometimes it means that you miss some easy ones on the next question. And we are looking not to complete every question, but to get as many marks as we can. So very often it is time to just stop a question and go, I must move on. I'm spending too long doing this. I normally ask my students to look at the paper, open it, and flick through it. Have a look. How many pages? How many questions? Where is about halfway? And I ask them to find the thank God question. The thank God question is the one is thank you, God, for putting this question in because I revised it last night and I know all about it. And it is not just so you get a lot of marks on that question. It is because this will settle you down, make you more confident, and a confident student does better. So you are looking at the paper, you're thinking 1.5 minutes per mark. Here's a nice question. I know all about it. It's 8 marks. I've got 12 minutes to do this. That's fantastic. I can relax. Thank God this question is here. I know it. I can do it. And then I stop and I move on. And now I am more confident. And the other thing is, Sometimes you will look at a question and you can spend many minutes trying to do it and not being able to. Leave it. You cannot answer every question. You cannot. You will not get every part of every question right unless you're an exceptional candidate. Most of us do not. So I'm saying sometimes if you get to a question and you go, I don't know what this is about at all, leave it. But the two asterisks are, I get my students to put asterisks in the side by the question. So later when they are getting towards the end of the time, they look through the paper, asterisks. This is a question I thought I could maybe come back to later. You know, I didn't do it. I didn't know what to do, so I'll get it now. So rather than you having to read and going, yes, I've done that. No, yes. If you put big stars in it in the paper, you know that's what you're looking for when maybe you have 10, 15 minutes left at the end. So try to think how to make the best, get the best number of marks. And this is it. Okay. This is a way to make the best number of marks. If you, we will look at more exam questions, but these are very important basic exam style knowledge. Okay. Know how many minutes you have for a particular question. Look at the question carefully, check that it's 1.5 minutes per mark on this paper. If it's 120, if it's 2 hours and 80 marks, that's 1.5 minutes per mark. And don't forget, you mustn't, the third bullet point here, do not spend too long trying to get the last marks on a question. It is better to move on and pick up the easier marks at the beginning of the next question. Find your thank God question, do that first to make you feel confident. Okay. There are 3 types of calculation questions in enthalpy. Okay, 3 types. We looked at the first one last time, and we're going to do one of those first. And then there are bond energy calculations. The first 2 are easy. The third one, Hess's law, is not quite so obvious. And we will return to Hess's law another time, but we will try to do one today. So we're going to do finding enthalpy from the details of an examination. Then we're going to look at bond energy. Then we're going to look at Hess's law. So here we go. This is the one which, if you were here last time, we looked at. This is a typical, you might get this on paper 3. You might have to do an experiment like this on paper 3, where you are trying to find the energy given out or taken in. In this question, we have a small burner underneath here at the bottom. And this burner here contains some alcohol. It might be ethanol, hexanol, doesn't matter. And it is being used to heat up some water. We have to measure the water first. In this case, they have got 500 cubic centimeters. And you have to weigh the little burner before and after, so you know how much of the alcohol has been burned. And you get a set of data like this. If you're doing paper 3, you would need to collect this data. But in paper 1 or paper 2, this is what you get. The questions are like this. First, calculate the moles of methanol burned. Second, find the heat change. Last time we decided that this was called Q. Then find delta H, molar heat of combustion of methanol. That's the delta H. And then it says, oh, there's some errors in the answer. In other words, the number you came out with is not correct. What could have gone wrong? And then a thermochemical equation and then the energy level diagram. So mute, please. So what you have to do, and this is where I'm just going to rush through it for you here. So the first thing you have to do is to find Q. I'm just going to remind you of what we did last time. So Q is the heat change, and that equals the mass of water times C. C is the specific heat capacity of water. You are always given that, times delta T, the change in temperature. So the mass of water is here. It's 500 cubic centimeters, and it tells you it's 1 gram per cubic centimeter. So that number there is 500. C, you will always be told in the exam. You never have to remember it. It's 4.2. So there's 4.2. Delta T is the change in temperature, and you can see here it's gone from 20 up to 27, so it's 7. And that gives us a number. I'm not worried about what that number is at the moment, because the next thing we have to do is we have to work out delta H, and delta H is Q, this number that we have here, over N, where N is the number of moles. Okay, that's how you do all of these questions. Now, they might ask you, in this question they do, to work out the number of moles first, then Q, then delta H. It doesn't matter. Okay, so here it is. There, calculate the number of moles burned. Well, here we are. We know the mass at the beginning was 22.98 and afterwards 22.11. So we know that 0.87 grams has burned. So moles is grams over RMM, 0.87 over the mass of methanol. Q, we've just done. Delta H, I've told you how to do. So let's have a look at another one. Okay, this one's for you. This is for one for you to have a go at. Okay. This is the setup. This is exactly how you might be asked if you were doing paper 3. Okay. You have often a glass, but sometimes copper beaker with some water that you have to have measured. You measure the initial temperature. You weigh the alcohol burner. You set light, you put it out, you weigh it again, and you look at the thermometer. Okay, here are some, here's a practical detail of it. So here's one. This is, they're actually doing the practical. They're taking 100 cubic centimeters of water, putting it into the copper calorimeter. We won't watch it this time, but I will send the presentation to your teacher. So if you actually want to watch how it is done, then you can. If you need to do paper 3, this is quite a useful thing to watch. But we're not interested now because we're going to do the question. So here is some data that the student has collected. The initial mass of the burner, its hexanol, is 129.56, and at the end it's 129.20. So there's the mass used. They've calculated that for you, 0.36. The initial temperature was 19, the end temperature was 29, and we had 100 grams of water. Okay, so all I want you to do is to work out Q, the number of moles of hexanol, and the delta H. Okay, I'm going to show you, there's the data which you need. I'm going to add to that hexanol, the RAMs, carbon is 12, hydrogen is 1, and oxygen is 16. And C is 4.2 joules per gram per degree Celsius or Kelvin. Okay, so I'd like you to work out Q first. Q is equal to MC delta T. The number of moles is the grams over the RMM or RFM, and then, whoops, it should say delta H. Delta H is Q over n. Okay, so those are the bits which you need. Have a go. See if you can do it. I'd like to see everybody trying to have a go, because this is, if you can get used to doing this sort of calculation, then when you get to the proper examination, you will find it easy. Honestly, you will find a question like this and you will think, I can do that. And then you will feel confident. So let us have a go. Come on, Calvary, let's have a go. See if somebody there at Calvary or Glory could do the calculation. It is very useful calculation to be able to do. Kabiro, Mathari, St. Mary's, let's see somebody come up with an answer. If you need a hand at all, I will help. But let's just see if you can do this question. Start by doing Q. Q is quite easy. It was 100 grams of water. I'll just remind you of that. I'll write it down. Excuse me. So the mass of water is 100 grams. That was what is being heated up. So the first bit is very easy. As soon as you think you know the answer to Q, you can show me. Somebody has got, oh, St. Mary's done everything. Two. That's really good, St. Mary's. Who's that? Better not be Brian. Not Brian again. Brian, you've got a mask on. Good. Well done, Brian. Wamwini, it's a bit bright. Can you go a little bit closer? 4,200. Yes. Well done. Yes, that's very good. Well done, Wamwini. 4,200. Good. So we have several students who think that Q is 4,200. That is correct. If you think it is 4,200, that is correct. Be careful working out the RMM. If you make a mess of that, it is quite annoying. Some people are doing very well. I can see that. That's really good. Don't forget that it should be in kilojoules per mole at the end, not joules, because the answer in Q will be joules to start with. I'm going to move on in about 1 minute, so see if you can get there. If you have the answer and you know it and you are confident about it, it would be good if you went and you found somebody in your classroom who is finding it difficult and help them. Because that way we all get better, which is excellent. So if you know the answer, you feel confident about it, go and find somebody who is finding it difficult and help them. Okay, I'm going to look at the question now. So here we go. So the first bit is finding Q. So Q is the mass. It's important to remember it's the mass of water heated times the specific heat capacity times the change in temperature. Whether the temperature goes up or down doesn't make any difference. So in this case, it is 100 grams times 4.2 times 10, because it went up by 10 degrees, which is 4,200 joules, or 4.2 kilojoules. Then we work out the number of moles. The number of moles of something which is weighed out is grams over RMM. It told us it was 0.36. And if you work it out for hexanol, it's 102. It's 102. And that gives us 0.0035 approximately. If you're doing a calculation like this, do not approximate. Don't take it off your calculator and put it back on again, approximated. Keep the unapproximated number. So the number is not 0.0035. If you do the calculation and you say, okay, 0.36 divided by 102, it comes out as a more complicated answer, 0.003529 and so on. So keep that on your calculator. Then delta H is this Q here over that N there. So it's 4,200 over 0.0035, which is around about that many joules per mole. But we don't do it in joules per mole. It has to be in kilojoules per mole. So it's 1,200 kilojoules per mole. Why is it negative? Somebody tell me why delta H has to be negative 1,200 kilojoules per mole. It's simple. Just tell me. Somebody unmute and just tell me why it has to be negative, because you will have good Mathari. And Mathari, somebody has just written exothermic. Absolutely right. Thank you. It's exothermic. So when we write the equation, we would write delta H equals negative 1,200 kilojoules per mole. Okay. Second type of question. This is about bond energies. I want you to look at this table now. It's a bit small, perhaps, but I want you to see some things which are quite interesting about it. Firstly, the single bond energies. They're normally in numbers up to about 600. It's a very, very strong bond, which is anything like 600. Many of them are 200, 300, 400. Okay. Then there are multiple bonds. So a double carbon to carbon, triple carbon to carbon, carbon to nitrogen. And this one here, Nitrogen to nitrogen, triple bond, 945. That is why nitrogen is very unreactive compared with oxygen, because oxygen only needs about 500 to break and nitrogen virtually 1,000. Something else which is quite interesting is that a carbon to carbon bond single bond is 346. Here it is, here. But a carbon to carbon double bond is 602. Now, if we said this is around about 350 and this is around about 600, then where is the extra 100? Well, this is because the second bond of a carbon to carbon double bond is weaker than the first. Sometimes people draw it like this, 1 and a bit. This is not correct unless you are thinking about its strength. And the same is true of the triple bond. The triple bond is not 3 times 350. It's less than that. And this is because the carbon to carbon single bond is between the carbons, and the carbon to carbon double bond happens in a way which is like a sideways overlap, and it is not as strong. So the second bond is weaker, which is why the alkenes are much more reactive than alkanes. Okay, let me just get rid of that. So I need you to remember those sort of things. Okay, now bond energies are always given as a positive number, always. It's always given as a positive number. And the positive number is the amount of energy needed to break them, okay, to break them. And there's a very simple way of remembering this. And that is that you need to remember this if you don't already know it. Breaking bonds is endothermic, okay? Breaking bonds is endothermic. You think about it, if I want to break a table, I have to put force in to break the table because the bonds hold it together. But that means also that therefore making bonds must be the opposite of that, and it's exothermic. So if I have a carbon to carbon single bond, if I took that and I broke it, that would cost me 346 kilojoules per mole. But if I took carbon and I made them into this, it would give out 346 kilojoules per mole. It's exactly the same number, it's just opposite. And I have said this to some classes before, you may not have seen this before, but my way of remembering this is this. It's bendomexo. Bendomexo. Breaking is endothermic and making is exothermic. Bendomexo, 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 bendomexo. Remember bendomexo because this is how we do these questions. Okay, so here we go. So this is what happens in a chemical reaction. This is methane burning. And energy goes up the side and along the bottom is the progress of the reaction. So here's methane, here's oxygen, and it turns into carbon dioxide and two waters. But on the way, it had to break into separate atoms. They look like they're joined. They're not. Carbon and 4 hydrogen and 4 oxygen. And then they recombine to make carbon dioxide and water. And we normally see this as a line that looks like this. That's what the energy profile looks like. Okay? So we would normally have it very simply like that. Okay, so in this sense, it goes like this. There's energy up the side, It's normally progress. If you're asked to draw these yourself, progress of reaction along the bottom. And we have CH4 plus 2O2 here. And then we have to put energy in to get it to react. And then it drops down the other side to form CO2 and 2H2O. Now, the difference between this and that is the delta H. And this delta H is negative 890 kilojoules per mole. This here, you probably remember, is called the energy of activation. That's the amount of energy needed, the particles need before they can react. That is the amount of energy they need to break into a carbon and 4 hydrogens and mute, please. Thank you. So at the top, it is all broken, and then it comes down the other side. In other words, going up this side, we are just breaking bonds. That's the bendo bit. And coming down the other side, we're making bonds, and that's exo. So let's have a look at a calculation and see how it goes. Oops, sorry. I just need to get rid of this. Okay. Here we go. Here's an equation. This is the dehydration of an alkanol called ethanol. If ethanol has water removed from it, it becomes ethene, an alkene. So the way you do this is to draw out all the bonds and then remember bendo-mexo. So let's have a look. So I've drawn out the molecules, and then I need to count each type of bond broken then made. So here's the broken. I write on one side the broken ones, then the made ones. These are endothermic, these are exothermic. So I'm going to break the carbon to carbon single bond. That is worth 347. And I'm breaking it so it's positive. This is really important that you concentrate on this bit. Then I'm going to make a carbon to carbon double bond. That's worth 617. And it's made so it's exothermic. I also break the carbon to hydrogen bonds, and there are 5 of them, and they're 5 times 413 each. So that's 3,237, and it's positive. Why? Because it is being broken. On the other side, I make a new 4 carbon to hydrogen bonds. That's 4 times 413. It's a total for this side, total for that side. I also have to break the carbon oxygen bond here. And I have to break the oxygen hydrogen bond. And on this side, I have to make 2 OH ones. There. Then I total them. So everything on this side is 3237. Everything on this side is 3203. These are positive. These are negative. Then I just total them. So I say 3237 minus 3203, and it comes out as negative 34. Negative 34. That means it's exothermic by this small amount. Here's one for you. What's the enthalpy for the combustion of propane? Here are the bonds. Here's the equation. Here are the pictures. Now you have to do this quite carefully, but you have to count up all the bonds you're going to break. So for instance, in propane, down here, I'm going to break 1, 2 of these. I'm going to break 1, 2, 3, 4, 5, 6, 7, 8 of these. Do you see what I'm doing? Okay. So let's see if you can do it. It's it it's quite painstaking. You have to be careful that you get it all right, but basically that's how you do it. Remember that everything on the left-hand side will be bendo. Okay, everything on this side here will be positive, and on this side it's mexo, so it'll be negative. So see if you can total those up. It's quite difficult to get it right. It's easy to miss something, but you see if you can do it. If you're not sure what to do, I'll show you in just a moment. Okay, if it's a bit confusing, if it's not entirely obvious to you, I'll show you in a minute. But if you're doing it and it's okay, I suggest you write down the formulas and you calculate how many of each you need to do while I go back and show some other people. If you just put your hand up, if you find this difficult, if you're not sure what to do, just put a hand up and I will come and show you again. So does anybody want me to go through it again? No. Oh, yes, some people at Wamuini. Thank you for being honest. Good. And Mathari. Okay. Let's see if I can just show you once more. I'm going to do it quickly. Sorry for stopping people looking at this. If you can take a picture of this with your phone, if you've got one, then you'd be able to write down what you need, or just draw out this. If you can take a picture, then you'd be able to hang on to all the numbers while I go back a stage. So I'm going to go back a stage. Okay, let's here. So what I do is I try to work out what I've got to break and what I've got to make. So between these two, it's going to turn from this chemical in the left into these ones here. So I'm going to break, oops, what's happening? I'm going to break, whoops, break one carbon-carbon. There it is. So I suggest you go like that when you've done it. Okay. I'm going to have to break 1, 2, 3, 4, 5 carbon to hydrogen. I'm going to have to break 1 CO. 1 CO. I'm also going to have to break 1 OH. 1 OH. Now I'm going to look at what I'm going to make. So I'm going to make one of those. 1 C double bond C. I'm going to make 1, 2, 3, 4, 4 C H. I'm going to make 1, 2 O to H. It doesn't matter whether it's H to O or O to H. Okay. So I would then find all these numbers, okay, multiply them as necessary, and then total them, and total them here. These ones will be plus because bendo, they're being broken, so they're endothermic, and endothermic means it's plus. And then these guys are mexo, so it will be negative, and then I just join them together. Okay, so I'm now going to go back to the next question. Okay, here we are. So this is what you're trying to do now. So just like the one before, so I'm going to bendo, I'm going to break 1, 2. So I'm going to need 2 of those. And I'm going to need 1, 2, 3, 4, 5, 6, 7, 8 of those carbon to hydrogens. And I'm going to break 1, 2, 3, 4, 5 of those there, and so on. Okay, so I'm going to add all those up, and that will be a positive number. And then I'm going to do the same over here, only this time I'm making 1, 2, 3, 4, 5, 6. Oh, 6 of those. That's quite a lot. And so on. Okay, so everybody have a go. A little bit closer, please, Brian. It will be about that number. I haven't got the answer in front of me, but it will be a number like that. Well done. Good. Anybody got an answer at Wamawini? Anybody at Calvary? Glory seemed to have gone. Anybody at Mathari? Anybody at Kabiro? Brian, you can show your co-students now. Show them how to do it if they're not sure. Somebody in the front at Wamawini knows what they're doing. Very good. Calvary, it is a really good idea to actually have a go, to actually get a calculator and have a go. I can see that you know what to do, or at least it looks like you know what to do, but to actually practice it is very important. Come on, Stacey. Where's the answer? We will go through this in just a minute.
No, no. Hold it up.
2 more minutes. Oh, what is happening? Okay. I'm going to do it now. So you got 30 seconds. Quickly, Mathari. Does everybody get it at St. Mary's now? Does everybody understand now, Brian? Cool. Well done. Oh, one weenie. Show me. Little bit closer, please. Oh, nearly, nearly. Gosh. What's your name? Write your name. Felix Turner. Well done. Well done. Okay, I'm now going to do it. So you carry on working if you want, but I'm going to show you how it goes. So here we go. Here's the numbers. Here's the chemicals. So I have to break 2 carbon to carbon, 694, the two 347s, 8 carbon to hydrogens, 3304, 5 oxygen, double bond oxygens, 2490. So the total of the breaking comes to 6488 plus positive 6488. The making is easier because we've got 3 carbon dioxides, that's 6 of the C double bond O's, which is negative 4470, and 8, that's 4 4 waters, which makes it 8 HOs, 3736. So the total maxo is negative 8206. So when we combine those two, we find the answer is negative 1718, 1718 kilojoules per mole. Okay, so just look at it, understand exactly what we were doing, and you will be able to do this. It will not be as complicated as this one. It will not be. I'll just show you something funny which came up in an exam here. They asked the question, what? So this is an alkanoic acid, and you may not have come across alkanoic acids yet. When they react with alkanols, they form something called an ester. Okay, and the ester looks like this. It's very sweet smelling, lovely sweet smell, like this. And they said, looking at these molecules, why is delta H 0? Well, if you look at this, the bit which has changed is this here. That was this bit here. So we had to break off that. And we also break off this. And we make this. So we are breaking 1 oxygen to hydrogen here. And we're breaking it off here. And we are making exactly the same number. So we're making the carbon to oxygen here. We're breaking carbon oxygen there, making it here. We're breaking and making exactly the same number of bonds. If you calculated all of it, you would come out as bendomexo is 0, which is quite weird. Anyway, right, next bit, last bit before we run away and go, oh, chemistry is so hard. Okay, this is Hess's law. And Hess's law is sort of really simple in its ideas are very simple, but it can look rather complicated. And I'm going to show you how it goes. If I take a chemical like, say, this is called ethene. And if I turn ethene into ethanol, like that. No, I'm going to change it slightly. Oh, no, it's okay. And I turn it into ethanol. It doesn't matter whether I do it like this, which has a delta H, or if I turn this first into something else, like, for instance, ethine, and then I make ethine into ethene, and then into ethanol. It doesn't matter whether I do it this way either. Delta H1, delta H2, delta H3, delta H1 is equal to delta H2 plus delta H3. Now, when I did this, when I was trying to explain this before, not today, in another lesson, what I did was I said, let's imagine that we are making a journey. And the journey was from Nairobi to Malindi. Okay, this was my example. So I'm going from Nairobi. I'm going to go to Malindi, up the coast, lovely place, been there. And I'm going to do that. So you can use the main road, which goes that way, or I can go via Mombasa. I can go from there to Mombasa, Mombasa to Malindi. Now, if I'm trying to get from Nairobi to Malindi, it is important that I know which tickets I have to use. So I have a ticket here from Nairobi to Malindi. If I have a Nairobi to Mombasa ticket, that's fine. But if I also had not a Nairobi to not a Mombasa to Malindi, but my return portion, in other words, if I had this journey, whoops, sorry, that's not a very good line, but anyway, you know where I'm going, then this is no good to me. If I want to go from Nairobi to Malindi, and I've got a ticket from Nairobi to Mombasa and one from Malindi to Mombasa, the guy in Mombasa will not allow me to get on the bus. He say it's a wrong ticket. I need that ticket. But if you remember what I said about bendomexo, one change can be opposite of another one just by changing its sign. So let's say this is 1,000 kilojoules per mole. And let's say this is 2,000 kilojoules per mole. And let's say this is 1,000 kilojoules per mole. It is not true to say this one equals that one and that one. That doesn't make any sense. That doesn't make sense. All right? That's really important that we know that we've got to reverse this one here. Okay? So let me just reverse it. So we've got this one here. I've got to reverse it. Instead of it being 1,000, I've got to change the arrow. It's got to go backwards and it's got to change to negative. Then 1,000 is 2,000 minus 1,000. In other words, delta H1, that's that one, is equal to delta H2. and delta H3 reversed minus delta H3. Change the arrow direction. Here it is. This is the sort of question we get. So we're trying to find the energy change for nitrogen and hydrogen making two ammonias, okay? But they've given you all this data down here. Now, if you already know how to do this sort of question, just have a look at it, have a go at it while I go through it, okay? If you look at this lot down here, it doesn't seem to be very useful because I've got some information about nitrogen. Okay, let's just pick up let me just get a highlighter. So if I'm looking for something to do with nitrogen, I can find nitrogen in this equation here, but I can't find the rest of it. Well, hang on, where is the rest of it? Well, let's change this. This hydrogen turns up in this equation here, but the ammonia doesn't. So hang on, let's just try and find something else. Okay, where's the ammonia? Oh, look, there's an equation with ammonia in there. Now, if I look then at the chemicals which I've got in the products, I've got nitrogen monoxide, nitrogen 2 oxide, and water. So this side here and that side there both produce 2 NOs and 3 waters. In other words, I know that and I know that. And what I'm trying to find is this. So let's see what happens next. Here we go. Here's the information. Here's the equation. Okay. So here's the nitrogen, and I've got some information. But all of these equations produce the same chemicals, NO and water. I know this first equation, N2 plus O2 makes 2NO. Here, it's that arrow. And I know that the value is positive 181. I know the second equation is hydrogen making water. There. And I know the third one is ammonia and oxygen making NO and water. That equation there in the opposite direction. Now, Hess's law says from the left-hand side here to the right-hand side, I've got to be careful. I've got to make sure all the arrows go in the same way. So if I'm going from Nairobi to Malindi via Mombasa, I know all the arrows have to go. That one is the same as all of these going in that direction. In other words, I've already turned this one round. So let's see what happens. So I know this one. I know this one over here is 181. I'll just go back. I'll just label these for you. So I know this number, this one here is from the first equation. It tells me this is 181 and it's positive. The second one is for hydrogen making water. That's negative 286. But I need, because I've got 3 of them, I need 3 of those. And I know that this one over the other side, I've actually reversed this one at the bottom. So it was negative 587, but now I've reversed it. So I just change its sign. Whoops, sorry. Come on. Oh, come on. I just see if I can do this. change its sign. So now it is the 181, 3 times the 286, plus the 587. And that gives me the answer, which is negative 90. Now, a lot of people will look at that and think, I cannot do that. But you will be able to. So what I want you to do, I'm going to show you just in the last few minutes, show you another example, and we'll see if it makes sense. So in this one, we are trying to work out methane burning in oxygen. Now we know the answer is about 890, carbon dioxide and water. Here's the data I have. Carbon and hydrogen makes methane. Carbon and oxygen makes carbon dioxide. Hydrogen and oxygen makes water. So in this case, the thing which is common to both sides is that both sides, it's always can make or are made from. So in this case, we have arrows which go from this chemical here at the bottom up to that, and up to that, and up to that. And I want this. So let's see if anybody can think about how we can do this. Remember that if I start Nairobi, Malindi, and I want to go via Mombasa, I want to go down this arrow and then up again. So this one here, whatever that value is going up, I'm going to have to change its sign. So this one at the moment going up on the left-hand side is negative 75. Think about what I need to do with that. To make carbon dioxide here, it's negative 394. To make two waters, it's 2 times negative 286. So you think, how do I find the question mark? How do I find the question mark? If I start at the left at the top and I need to go to the right on the top, then I can either do that in one step or I can do it. I'll just use a highlighter to show you what I'm going to do. I'm trying to find that. Okay, so I may need to change the direction of some of the arrows. We've only got a minute. Just see if you can get anywhere. Here are the arrows with the numbers. So what do I need to do? What do I need to do? Would anybody like to tell me what I need to do? To find the question marks, what do I need to do? Well, it's time to go, so I'll show you. This arrow is in the wrong direction. So what I need to do is to reverse this arrow. If I'm going to reverse this arrow, then I'm going to change this sign. So I need to reverse this arrow here. In reversing this, I need to change that from negative to positive. Now what I have is 75 plus negative 394 plus negative 572. That's that. And that will be my answer. Okay, so in these, all we have to do is to find what is at the bottom and then find the arrow or arrows I need to change the direction of. Okay, the point is that that direction is the same as that direction. So this arrow here was wrong. Okay, I hope that is helpful. I hope that is helpful. Okay. That has been really quite a difficult lesson.